Hi, I am Marco Giordano, and with my colleagues Philip Meyer and Michele Magno, I would like to introduce you to our paper, a battery-free long-range wireless smart camera for face recognition. Here I am with a piece of the ALHC. It's the world's largest particle accelerator in the world, and it's also one of the most radioactive places on Earth. Radiations can have destructive effects on electrical components and has to be taken into account in many use case scenarios, as in medicine and aerospace. The particle accelerator is placed 100 meters under the Earth, and as you can see, there are not many cables around here. In fact, pulling cables is extremely difficult and expensive. Moreover, drilling holes in the walls of the tunnel can cause radioactive dust, which is pretty dangerous. And as you can see, there is always lights on the whole time. So this one is a perfect use case scenario for our wireless node.
Let's now have a look over the different domains of our wireless sensor node. For the sensing domain, we choose an ultra-low power camera from Emax, capable of delivering 320 x 240 pixel images in just 2 mW of power consumption. As far as wireless goes, we choose to use LoRa for its long range and low power capabilities. Thanks to the neural network run at the edge, we transmit only 1 byte of data, so low bandwidth is really a non-issue for us. In our work, we compared 2 microcontrollers, one from Atmel with excellent performance under radiation, and one from Magno, which is the most energy-efficient Cortex-M4 on the market, perfect for wearable applications. To power our board, we choose a state-of-the-art energy harvester with maximum power point tracking and low leakage and low SDR storage capacitor. Self-sustainability for neural network inference is a challenging task. A microcontroller has limited resources and long running times in active mode, thus the components were selected on base of their low power performance. Now let's delve into how the device functions. We start with the capacitor completely emptied and current is not delivered into the system until the cold start is finished. As soon as current is delivered, the whole system is put into sleep mode to reduce the overhead on charging as much as possible. The harvester has a voltage comparator with a settable threshold that we use to fire an interrupt. When we receive such confirmation, we turn on a time-of-flight sensor that will periodically check whether a person is near the device, while the rest of the system is put back into sleep mode. In case a person is detected, the microcontroller is waked up, a photo is taken, and a neural network is run. The end result is then sent over the LoRa to a gateway that can forward it to a central server. The camera shoots images at a resolution of 320 x 230 pixels, but the neural network processes photos with a resolution of 40 x 30 pixels. This size has been chosen as the best trade-off between the model's memory occupancy and computing time over a very moderate loss of accuracy. The model is composed of convolutional and dense layers with ReLU and a softmax activation function. The neural network is composed of less than 40,000 parameters and requires only 30 mJ of energy per inference. We choose to quantize the weights of the network to 8-bit integers as the best trade-off between running time and accuracy. We are thus able to achieve more than 90% accuracy over a 5 classes classifier in less than 650 milliseconds of inference time. In the confusion matrix, we can see how the correct guesses on the diagonal are the vast majority, while the missed guess phases are very few and pretty balanced among classes. A key to achieve such performance has been data augmentation. In fact, our dataset had few images per person, about 20-30 per subject. In particular, we applied a rotational transform to images from -20 to +20 degrees in steps of 10, and applied a gamma transform to generalize towards different exposures. Let's now focus on the power performance and the battery-less operation of our device. Starting from the current profiling, we can clearly see the different operation performed. It starts with a measure from the time-of-flight sensor that wakes up the microcontroller. An image is subsequently taken from the camera, the neural network is initialized, and inference is performed. In the last part of the diagram, the inference results is sent over LoRa, and the node is put back to sleep. We can now see the voltage across the storage capacitor plotted against time. We can distinguish two charging profiles, one from 0 to 1.8 volt and one from 1.8 to 5 volt. The charging time of the latter is much shorter, thus we dimension the capacitor to stay always in this area during operation. It is also clear how the Apollo 3 implementation is much more energy efficient than the SAMD51, and is thus perfect for applications with short delay time between inferences. On the other hand, the SAMD family has shown great performance under proton and gamma radiation, a requirement in some specific use case scenarios. This is the demo of our product. As you can see, here attached to the door with some space-grade material, which is definitely not tape, is the wireless sensor node, while here on the desk there is another board equal to the previous one that acts as a gateway. Let's see if this thing works. We just showcase how our wireless node can perform a 5 classes recognition over faces or memes.
In this work, we showcase a battery-less wireless sensor node that can run inference of neural network at the edge and start with as low as 250 lux of indoor lightning. I hope you had a great time, and thank you for your attention.